Welcome to the Explainer. Today, we're going to crack the code behind pretty much every number you've ever used. We're diving deep into the very building blocks of mathematics to uncover a rule so powerful they had to call it fundamental. So let's just jump right in with a big question. Are numbers just these random things, or do they have some kind of hidden structure, a unique identity? Is there something like a fingerprint for the number 12, or maybe 1200, that makes it what it is and nothing else? Well, the answer is a huge, resounding yes. It all comes down to one of the most elegant, beautiful rules in all of math, and it gives every single whole number its own unique DNA, a code that absolutely cannot be faked or copied by any other number. Okay, so how are we going to crack this thing? First, we'll get a handle on what this numerical DNA actually is. Then, we'll explore why its uniqueness is such a game changer. After that, we'll see what kind of mathematical superpowers it gives us. And finally, we'll dig into why it earned the name fundamental. All right, first up, what exactly is this secret code we're talking about? Well, it all boils down to a special class of numbers I'm sure you've heard of, the primes. So here it is, the big idea. Any whole number bigger than 1 is either a prime number all by itself, or it can be broken down into a specific set of prime numbers multiplied together. You can think of prime numbers as like the unbreakable atoms of the number world. Let's take 240, for example. You can break it all the way down to its prime building blocks. And here's the cool part. No matter how you start, no matter which factors you pull out first, you will always end up with 4 2s, 1 3, and 1 5. That right there, that specific collection of primes, that's the unchangeable identity of 240. Now, I've said it a couple times already, but the most important word in that whole definition is unique. Seriously, it's the key that unlocks the real power of this theorem, and it's what brings a beautiful order to the entire world of numbers. So why is that such a big deal? Well, if you use any old numbers to break something down, numbers that aren't prime, what we call composite numbers, things get messy. You can actually get different answers. Let's say we want to factor the number 12. There are a couple of ways you could go about it. And you can see it right here. If you use composite numbers, you could say 12 is 2 times 6, or you could say it's 3 times 4. Both are correct, but they're different. But when you break it all the way down to its prime factors, there is only one possible combination, 2 2s and a 3. The order might get shuffled around, sure, but the set of ingredients is always, always the same. And that, right there, is the beautiful guarantee of the theorem. It's a mathematical promise that the prime recipe for any number is absolutely one of a kind. This incredible stability is the bedrock that a huge amount of number theory is built on. So, okay, it's a neat trick for organizing numbers, but what can we actually do with this code? Well, it turns out this theorem isn't just some abstract idea. It's an incredibly powerful tool for solving real problems. This theorem gives us a mathematical superpower, a simple, totally foolproof way to find the highest common factor and the lowest common multiple of any group of numbers. See, once you break numbers down to their prime DNA, you can easily see what they have in common and how they relate. Let's see it in action. Okay, let's look at 850 and 680. Once we have their prime DNA laid out, finding the highest common factor, or HCF, is as easy as just picking the lowest power of the primes they share. So in this case, that's 1 2, 1 5, and 117. Multiply them together, you get 170. Simple. For the lowest common multiple, or LCM, you do the opposite. You take the highest power of every prime involved. That gives us 2 cubed, 5 squared, and 17, which comes out to 3,400. It's a clean, elegant method with zero guesswork. So this brings us to the big question. Why isn't this just called, a neat theorem of arithmetic? Why did mathematicians give it such an epic title, the Fundamental Theorem? Well, because this idea has been a cornerstone of math for literally centuries. The ancient Greek mathematician Euclid was already laying the groundwork for it over 2,000 years ago. The concept got sharper over time, and then in 1801, the legendary Carl Friedrich Gauss just sealed the deal with the first rock-solid proof of its uniqueness. And its importance is just huge. For one, it's the real reason we don't consider the number 1 to be prime. It also gives every number a standard official form, or a canonical representation. But here's what's really wild to me. This whole unique factorization thing, it doesn't even work in all number systems. There are these other mathematical worlds where a number can be broken down in multiple different ways. The fact that our integers have this unique property is what makes our system so stable and predictable. Just think about it for a sec. If 1 was a prime number, you could just keep adding it to any factorization forever. The number 6 could be 2 times 3, or 1 times 2 times 3, or 1 times 1 times 2 times 3. You get the picture. That all-important rule of uniqueness would be totally shattered. So, sorry, Juan, you gotta sit this one out.
So what does it all mean? It means every number greater than 1 has its own special prime signature, fingerprint that belongs to it and it alone. This theorem is the simple, powerful, elegant rule that brings perfect order to the infinite, chaotic world of numbers. And that kind of leaves us with one final thought. The fact that there's such a beautiful hidden order in something as abstract as numbers really makes you wonder, what other fundamental codes are out there in our universe, just waiting for us to find them?